their toxicity. Let us mention SAR. There is no question. So when we look at our SAR, we are saying now we have agreed, when we look at all those structures, that is our general structure. So that is our general structure there. And as we have our general structures, we are saying there is that X atom, and we must have, as you have seen in all those compounds, you require 2 aromatic groups joined to an X, and then there is an alkyl chain which can have either 2 or 3 carbon atoms, and then you have our nitrogen, which should be actually a tertiary nitrogen for maximum activity. So when you look at these, are most of the compounds that we have, we are saying the AR can either be an phenyl, it can be a benzyl ring, it can be a pyridyl ring. So it can be an phenyl ring, it can be a pyridyl ring. All in some of the compounds, one of this can be a benzyl ring with retention of activity. Again, we see the different examples as we look at the specific groups. And then R1, R2, usually they are usually methyl groups, but this is where we have said they can also. So they can be methyl groups, part of a heterocyclic ring with retention of activity. And of course, also here, then this nitrogen is what we have said, it can be part of a heterocyclic ring with retention of activity. And we are talking about piperazine, we are talking about piperidine or piperazine. We are talking about piperidine with retention of activity. So that is a general structure of our antihistamines. Of course, we have, of course, mentioned that some of these carbon atoms and the nitrogen can be part of a heterocyclic ring. The heterocyclic ring mainly because of that nitrogen with retention of activity. When we say that, that will include the piperidine derivatives. It will include the phenothiazine derivatives, whereby you have the carbon and the nitrogens can be part of heterocyclic rings with retention of activity. So let us now look at just the common structural features. We look at the common structural features so that now when we go to the specific groups, I hope we remember some of these structural features. So what have we said? We have said those aromatic rings must be there. They can be substituted or non-substituted. So they do not necessarily have to be benzene rings, but they can be substituted, as you see in some of the compounds. They can even be heterocyclic. One of these rings can be a heterocyclic ring, can be substituted with a chloro group, with a bromo group, with retention of activity. Have the spacer, that spacer there, which we have said it can be saturated, it can be unsaturated, especially in the propyl derivatives with retention of activity. Then you have R1 and R2. We have said mainly when you have tertiary amines, you have best activity. And of course, we have also said you can have heterocyclic rings with retention of activity. So we are saying number 1, 2 aromatic rings are essential. They must be connected to a central carbon, nitrogen, or oxygen. You have the 2 central rings, which must either be connected to a central carbon, their nitrogen, or an oxygen, all on an oxygen with carbon, nitrogen, all oxygen. And then also the amine or the amino group is also essential. 2 aromatic rings, essential. They must be connected either to a nitrogen, to a carbon, to an oxygen. And then, of course, also you must have an amino group, or you must have an amine or a nitrogen. That nitrogen is essential. Between central atom and the amine. So when we look at this spacer, is that spacer between the central atom and the terminal nitrogen is usually 2 to 3 carbons in length. It can be linear. We have mentioned that. It can be a heterocyclic ring. It can be branched. It can be saturated or unsaturated. When we look at the specific compounds, what I need you to do is come back to this point. And for linear, give example. For ring, for branched, give example. For saturated, unsaturated, give example. We are only now saying it very generally, that spacer, it can be linear, it can be a ring, it can be branched, it can be saturated or unsaturated with good activity. Then the amine is substituted with small alkyl groups and is proteinable. So it is substituted with small alkyl groups. But we have, of course, said it can be part of a piperazine ring, it can be part of a piperazine ring, and even when it's part of a piperazine ring or a piperazine ring, it is still protonable. So one of the most important things there also to notice that nitrogen must be protonable. It must be protonated at physiological pH. Again, the final one, chirality at X. Chirality at this, when you have this as a carbon, then you have that, and you, as I said, has these two are not the same. X is a carbon and it has a hydrogen, and that group, you can have chirality. Chirality and having the rings in different planes increases potency of the drug. So we are saying that this ring and that ring should be non-coplanar. They should be non-coplanar, and when you have X in a manner, or X can be able, this carbon here or that atom there can be able to exhibit stereochemistry, then chirality or the stereochemistry has a role to play in the activity of these drugs. Hope that is. Those are just very general. We're looking at them very generally first, so that when we look at them generally, then when we go to the specific, we will be able to understand. So what are we noting? We are saying you can vary AR1 and AR2. You can vary AR1, you can vary AR2. You can vary the connecting, this. You can vary the connecting moiety. You can vary the connecting moiety. You can vary the substituents on the connecting moiety. You can also vary the substituents at end. So you can vary R1, R2. You can vary the connecting moiety. You can vary the substituents of the connecting moiety, because we have talked about piperazine ring, piperidine ring, and aliphatic groups. You can vary the substituents on the nitrogen, and that is what will account the variation that you put here, the variation that you put there, the variation that you put there. That is, of course, what is accounting, one, for the classification of these drugs. And at the same time, it will account for the differences observed in the potencies in the different classes, as well as the pharmacologic, metabolic, and adverse reactions. So the kind of drug you have, which is dependent on AR1, AR2, dependent on X, dependent on that, is the groups that you put are the ones that will be responsible for the potency of that drug. And we're going to look at that, the potency, how it's going to go undergo metabolism, whether it will have a lot of CNS effects, like it cause sedation, and so on and so forth. So of course, that only is saying the classification, the class of the drug is important in potency. It is important in the metabolic process or metabolic pathway, and of course also it is important in the adverse reactions. Let us now look at those groups that we have mentioned. We have mentioned the first group, and the first group is either the two aromatic rings. They are bulky for sure, and these aromatic rings, these provide bulk producing antagonistic activity. Remember, if you look at histamine has an imidazole ring, not very bulky. So now you bring in a still aromas, you introduce, you still retain the aromaticity that is found in the imidazole ring, but you bring in bulky groups. And once you bring in bulky groups, you introduce the antagonistic activity, agonist activity. So when you look at all these drugs, they have that bulky group, because if you do not make them bulky, then you will introduce agonist activity, and that's not what you want. Generally, you must have two aromatic rings. They can be phenyl, both. They can be one phenyl and a benzyl, or you can have an isoster such as pyridyl, and usually pyridyl gives compounds that are more potent. So when you have, let's say, like one phenyl ring and one pyridyl ring, or one benzyl ring and one pyridyl ring, when you introduce a pyridyl ring, which is isosteric to the phenyl ring, you increase the potency of the resultant groups. One of the important things, as we have seen, the two groups must exhibit non-coplanarity, and that is responsible for maximum activity. If fused, they must be also non-coplanar, as in the three ridge structures related to the TCAs and the phenothiazines. What we are saying is that even when you have the tricyclic derivatives like phenothiazines and the tricyclics, they must you retain the non-coplanarity, where the two phenyl rings are not in the same ring to bring about maximum activity. When those rings are substituted, para-substitution in small lipophilic groups increases potency and decreases metabolism due to decreased ring hydroxylation, especially when you do para-substitution with a halogen. And most of these drugs have halogen para-substitution. Like ofenadrine does have a methyl group, and the methyl group is ortho. But you find when you do substitution in any other position, you reduce the activity. Especially in ortho position, you reduce the activity. And the reason why you reduce the activity when like you do an ortho substitution is because you prevent the two rings by introduction of steric hydras. You prevent them to attain the non-coplanarity, maximum non-coplanarity which is required for activity. So if you do ortho substitution, as I have said, like in ofenadrine, you find that ofenadrine has minimal antihistamine activity, which can simply be explained by the fact that when you do an ortho substitution in any of those rings, you prevent them from attaining the optimum non-coplanarity that is required to bind the receptor. So para substitution is best. Ortho or meta substitution reduces antihistamine activity. The diarrhea pattern is present in both first and second generation antihistamine activity. So those, when you look at the first generation, we look at the second generation, we have said that generation is a derivative, so it should be there. So that diarrhea system is necessary for antihistamine activity. So that is what we are talking about. So in a nutshell, that is what we expect. That's the SAR we expect of the aromatic ring, AR1 and AR2. But as we look at the specific groups, we'll highlight the differences and the similarities. Then we look at atom X. Atom X, as I have said, is a connecting central atom. And atom X can be an oxygen, as we have said. It can be, of course, it is not usually purely an oxygen because there is a carbon. So it's unusually a carbon oxygen. A carbon oxygen, and then it can be a nitrogen, or it can be a carbon which links the side chain to an aromatic tail. An aromatic tail is this tail which contains the alkylamine. So it can be a carbon, it can be a carbon oxygen, it can be also a nitrogen with good activity. The nature of atom X is the basis for the structural classification of the H1 antagonists. The classical H1 antagonists are divided into 6 classes based on what X equals. X can equal to carbon, oxygen, which is the amino alkyl ethers, which we have looked at. And then, and again, if you're able to your handout, I don't know, you're able to look at it as you also have logged in. But now I hope you have understood. We are saying, and that's why I said we cannot call it just an oxygen, because there's a carbon oxygen, which is there. It's not like where you have a nitrogen or where you have a carbon. There's a carbon. The oxygen is not directly attached to the phenyl rings, because remember, the oxygen can only accommodate 2 bonds. If you attach it to the 2 phenyl rings, then you cannot attach it to anything else. So there is a carbon to accommodate, and then an oxygen, and then the oxygen is attached, of course, to the alkyl group. And when we have these drugs, when you have a carbon oxygen, we will further subdivide them into what we call the ethanolamines and the propanoamines. The ethanolamines is where you have 2 carbon atoms, and that's why we are calling them ethanolamines. The propanoamines, where you have clemastine and diphenylpyrrolene, is where you have 3 carbon atoms. The spacer has 3 carbon atoms, and ethanolamines, the spacer has 2 carbon atoms. Again, when we look at just a matter of I hope you can remember the drugs like carbinoxamine, but we are going to look at it later and give the good examples as we look at each class. So the ethanolamines, carbon oxygen, subdivided into ethanolamines and propanoamines. One has 2 carbon atoms, the other one has 3 carbon atoms. Then you have the propylamines, which again, as I had said, can be further subdivided saturated and unsaturated. For the saturated, you have chlorpheniramine. For unsaturated, you have triploridine. Those are just some of the examples. There are many, as I'd already given you. So chlorpheniramine for the saturated, triploridine for the unsaturated. Then, and that is when X is a carbon. X can be a nitrogen, and when X is a nitrogen, you can have the ethylene diamines. And again, we gave quite a number of examples. You can have the piperazines, because even if you look at the piperazine, N is still a nitrogen, the nitrogen, and you can have, of course, the others. You can have the piperazines, the cyclizines, the tricyclic piperidines, and phenothiazines. And of course, anytime you can also have other compounds, like where we talked about, of course, where you have it being part of like phenadamine, where you have it being part of a cyclic ring with retention of activity. This forms the 6 classes of traditional antihistamines and would include many of the new antihistamines, since they do not fall into one order traditional classes. I think that is the miscellaneous. SAR of X, what do we expect of X? If X is equals to a carbon, the antihistamines will exhibit chirality. For example, phenyramine and carbinoxamine. In that case, where chlorpheniramine, if you look at chlorpheniramine or phenyramine, it is able to exhibit stereochemistry because one of the rings is a ring and the other ring is a benzene ring. So that is why it is able to exhibit chirality or stereochemistry. For carbinoxamine, one of the rings is substituted, again being able to exhibit stereochemistry. S configuration has usually the S configuration have higher H1 receptor affinity, but we will look at the specific drugs and be able to mention the role or the significance of stereochemistry in these drugs. But all we are saying, why we have looked at X, we have the different X's, but we want to also highlight that when X is a carbon, you can have stereochemistry, and once you have stereochemistry, the stereochemistry will have an influence on the potency or activity of the resultant drug. Then connecting chain, it can either have 2 or 3 carbon atoms. No, not carbon, but it can have 2 or 3 atoms. That is the carbon chain. It's a carbon chain, so you can have either 2 or 3 carbon atoms with maximum activity. So note, it can be 2 or 3, not where, like when you were looking at the non-steroidal anti-inflammatories, we were very strict. It's either it's just 1 carbon atom separating the carboxylic group from the first hydrophobic group. So here we are saying it can be 2 or 3. And again, we will show the relevant examples. And of course, we have not talked about the ethanolamines and propanoamines. One is 3 carbons, one is 2 carbons with retention of activity. Its function is to separate the nitrogen from by 5 to 6 angstroms. I believe you have heard that measure. It is a unit angstrom. The unit angstrom, can you tell me what is the relationship between an angstrom and a meter? What is the relationship between an angstrom and a meter? What is the relationship between an angstrom and a meter? What is the relationship between an angstrom and a meter? Hey, class. Any response? What is the relationship between an angstrom? and emitter. Any response? None. Have you heard of the unit angstrom? Class? Have you heard the unit? Have you ever heard of the unit angstrom? Ever had class? Are we there? Oh, you've never had. That's good. So no, we haven't. Okay. So, okay. No, then if you haven't heard of it, then I will explain. So, an angstrom is a very, very small, and it is actually equal to 1 times 10 to the minus 10 of a meter. So an angstrom is 1 times 10 to the minus 10 of a meter. So a very, very small unit, very, very small unit, and it is what is used in measuring the bond length, used in measuring bond length, or used to measuring the space, like what we're calling the spacer. It has a length. That spacer has a length, and that's what you're saying. Its function is to separate the nitrogen from the rings by 5 to 6 angstroms. So that is the same as 5 to 6 times 10 to the minus 10 of a meter. So very, very small unit used to measure the bond length. So all we are saying is that we do require either two. We need either 2 or carbon atoms, and those 2 or carbon atoms which are between the X or the central atom and the terminal nitrogen are very crucial, because they give you the size or the length. They determine the size of the molecule, and you require a certain size of that molecule so that it can go and fit on the receptor and therefore be able to be responsible for antagonistic activity. We have said the connecting chain can be saturated, unsaturated, branch, or part of a ring. Branching decreases antihistaminic potency except for the phenothiazines. So in all the other drugs, you will find that branching decreases activity, with the exception of the phenothiazine, where the beta carbon is the beta carbon from the heterocyclic nitrogen. So this is, if you look at your phenothiazine, the in-between ring is a thiazo ring. A thiazo ring, it has a nitrogen and a sulfur. So that nitrogen, which is part of the thiazo ring, is is the reference nitrogen. So from that reference nitrogen on your aliphatic chain, you go first of all to alpha and then to beta. The beta will be the second carbon from that nitrogen. So the beta carbon branching increases antihistaminic activity, and we have an example, of course, of promethazine. But we are going to look at those examples when we look at each drug on its own. The basic aliphatic amine, so we're looking at those groups, what we expect of the different groups which we have said are most important, must be able to accept a proton. That means it must be a basic at physiological pH. I'd already mentioned that. So it has to be, must have a high pKa, R1 and R2. The potency order is a tertiary, higher than secondary, higher than primary. But tertiary amine, whether it's a tertiary amine by belonging or by being part of a heterocyclic ring, does not matter. Whether it's a tertiary ring, like if you tertiary amine, if you look at most of those drugs, you will find that that group is NCH32. If you compare that, if you look at the drug we call antazolene, unfortunately, I don't know whether you can see the structure. You will see that antazolene has a slight difference. Antazolene is a secondary amine, and therefore antazolene will have different, lower activity because of the fact that it's a secondary amine. So we are saying the amine must be a tertiary amine for optimal activity, for maximum activity. If you change it to you will not abolish, but you will reduce activity. Quaternary, quaternization, that means making it quaternary, whereby now it has 4 substituents, does not increase antihistaminic activity, but increases anticholinergic activity. Again, remember, when you talk about anticholinergic activity, the anticholinergic activity, the drugs that will bring anticholinergic activity will have structural resemblance to acetylcholine. And you know, acetylcholine has a quaternary amino group. So again, if you make it a quaternary group, If you make the nitrogen a quaternary group of course will be protonated, then you will move more to anticholinergic activity. Because of the barkenness of the molecule, it will not have cholinergic activity. Because of its barkenness, it will have anticholinergic activity. Why these drugs also have anticholinergic activity? Because when of the fact that in the body we say they are protonated, and since they are protonated, they have structural similarity with acetylcholine, they can actually go for the cholinergic receptor. But when they go for the cholinergic receptor, please do remember they will not trigger activity. They are too bulky. They will bring about anticholinergic activity. So there are those structural similarities, as we have said earlier, they are responsible for side effects, because these drugs are not selective for only the histamine receptor. They can also go for other receptors like the cholinergic receptor, to a very small to a very small level, the adrenergic receptor, and bring about a lot of toxicity. And that is why we have said the classical antihistamines have a lot of toxicity, because their structure allows them to go for other receptors. They are not highly selective. They can go for other receptors and therefore for other toxicities. So may be incorporated, this again we have said severally, into a heterocyclic ring, which is, although larger, the heterocyclic has constraint. Remember, we are saying when you incorporate this acyl chain into a heterocyclic ring, or heterocyclic ring are a bit constrained, and because of that constraint, that compound is still able to attain the 5 to 6 angstroms which you require for activity. Dimethyl is the optimal configuration to give us good, optimal activity. Larger substituents decrease antihistamine potency due to steric hydrons unless they are part of a heterocyclic structure when the link constrains the two ethyls so that they are still active. So we are saying, like for the aliphatic derivatives, methyl group is the best. It is responsible, dimethyl group or dimethyl amino group, responsible for maximum activity. If you add other bigger groups, you introduce steric hydrons, and whenever you introduce steric hydrons, that means that is not able to access the receptor optimally, and therefore does not give you optimal activity. As we have already said, when contained in a heterocyclic ring like piperazine, then you find that you have an ethyl derivative. You have an ethyl substituent on the nitrogen on both sides, an ethyl, but that ethyl group, because it's part of a ring, there is constraint. There is strain within that. There is strain within that piperazine ring or piperazine ring. Therefore, the whole molecule is still able to attain the 5 to 6 angstroms which you require for activity. So again, that is a basic aliphatic amine. Remember, as I have said, it must be protonated at physiological pH. I want us, those ones, the receptor drug interaction, we will look at it after we are done with the drugs. So with that, so what we were looking at was just the introduction to the classification. We can now be able to look at each and every class. But what we have learned, please carry it forward. We have talked something, we have said something about the AR1, the aromatic rings. There is non-coplanarity. They cannot be ortho-substituted, but they can be para-substituted. It can be a phenyl ring, it can be a pyridyl ring, it can be a benzyl ring. So I will need you to carry that information as now we move on. We have talked about the ethylene chain, we have talked about the terminal, the general SARs, which will apply across all these groups. But for each group, of course, we will look at what is necessary or what is applicable for that particular group. So we start with the first group, which is the ethylene diamine. Again, ethylene diamine, that is a basic structure. Ethylene 1-amine. That's what we're talking about. And these have low to moderate potency. Remember, we said the structure we have is responsible. The structure we have is responsible for the potency. They have low anticholinergic side effects. They will have side effects. This is protonated at physiological pH. It can go for the cholinergic receptors, moderate to high sedation. This is explained by the high lipid solubility introduced by these two groups. High lipid solubility, the molecules of these drugs penetrate the CNS and therefore bring about sedation. Examples of drugs is what we have here. So this is the general structure here. General structure there. If you look at these drugs, all of them, the ethylene-diamines, they have a benzyl ring. That's how you differentiate them from the others. You can't see there's AR and a CH2. So all of them do have the benzyl ring. Then the next ring, because remember we said there are two aromatic rings. The second ring is the one which can differ. The second ring can differ. This can be, X can be a carbon, Y can be a carbon. When X is a carbon and Y is a carbon, then you have phenbenzamine. And phenbenzamine is a prototype. X is CH, a carbon. X and Y are both carbons. And of course, this is a phenyl ring. So phenbenzamine, and you can see phenbenzamine, phenyl and benzyl amine. Phenyl, this is phenyl benzyl amine. So phenbenzamine is a prototype in that group, does not have very good activity, had very low antihistamine potency. So there was need for structural modification to see whether there could be structural modification to give us better activity. And the next group was the triple enamine. Triple enamine, again, in triple enamine, the difference is that this X is converted to a nitrogen, either X or Y, it doesn't matter because they're in the same position. So X converted to a nitrogen to give us ring. So Y, when you say one is a nitrogen, the other one remains as a CH. So that now it gives us the pyridyl ring, and of course that is to the phenyl, the benzyl ring. So that the benzyl ring is retained, and we will note, when you replace one of the phenyl ring with the isosteric pyridyl. Remember, isosteric pyridyl is when your nitrogen is either at that position or that position, not any of the other positions. So it must be either that position or that position, not any of the other positions. Then you get triple enamine, and triple enamine was found to have much higher potency. Then you have methylpyridine. Again, methylpyridine, again, is when you have the pyridyl group there, but, so you have the pyridyl group there, but your aromatic group, the phenyl ring, is replaced with the thiophene ring. Severally, we have said the thiophene ring, phenyl ring are isosters, so one can replace each other. Remember, all you require to retain is the aromaticity for retention of activity. So that can be replaced. The AR can be replaced with a thiophene ring, but of course that is already a pyridyl ring. We have explained why. Then you can also have thionzyl amine, and in thionzyl amine, two things have happened. In thionzyl amine, two things have happened. One, there is the benzyl ring. This too is retained as a phenyl ring. It's para-substituted. So the aromatic ring here, sorry, not this one, but here, the aromatic ring here is para-substituted with a methoxy group. So that is the thionzyl here substituted with a methoxy group. Remember, we did mention para-substitution does increase activity. And of course, the other difference is that in the thionzyl, then this is a nitrogen and that is a nitrogen. So we change from pyridine to pyrimidine. So we change from pyridine to pyrimidine, where that is a nitrogen and that's a nitrogen, and your aromatic group here has methoxy substitution. Then related compounds is what I said, anthazoline. When you look at anthazoline, please note, let me make it a bit bigger. I had mentioned anthazoline when it normally is used as nose drops. When you look at anthazoline, please note the difference. That is still our phenyl ring there. That is our nitrogen, and that is our benzyl ring. So here, the structure here is very, very similar to what you have in phenbenzamine. That structure there, very similar to what you have in phenbenzamine. But then now, if you look at phenbenzamine, it will have a CH2. But when you look at anthazoline, one of the carbons of the ethylene chain, part of a pyridine ring with retention not pyrolytic, but imidazole. These are midazoline ring. These are the midazoline ring. A midazoline ring, because of the double bond. If it didn't have a double bond, it would be a pyrolytic. But because of these double bonds, it has one. If it's an imidazole, it will have two. It will have that one, and it will have another one here to make it an imidazole. But now it's a midazoline. So now, of course, dihydro midazoline ring. So you have a double bond here, you do not have. So all we are saying is that this carbon, if you compare this with phenbenzamine, if you compare this structure with phenbenzamine, in phenbenzamine is CH2, and then attached to a nitrogen. You look at phenbenzamine, that, then CH2 attached to a nitrogen. If you look at antazoline, it has only one carbon as an aliphatic carbon. The second carbon is part of the imidazoline ring of activity. And we are not looking at this nitrogen here. We are looking at it's an ethylene diamine, because it is the two phenyl rings, the two aromatic rings are attached to a nitrogen. Then you have that CH2, and then you have this carbon here, and then you come down. Then if you look at this nitrogen here, we said maximum activity is obtained when you have a tertiary amine. This is a secondary amine. In antazoline, this is a secondary amine, and therefore you expect us to have slightly lower antihistamine activity compared to the other ethylene diamine derivatives, because it's a secondary amine and not a tertiary amine. So the decrease in activity is not because this carbon is part of a heterocyclic ring, but it is because in antazoline, the terminal nitrogen is a secondary amine and not a tertiary amine. So this is now just to give you the structure. That's phenbenzamine, as just as we have discussed. That's triplenamine. We have said triplenamine is where you replace the phenyl ring with a pyridyl ring with retention of activity. We reduce. Then we have meperamine, and in meperamine, again, we are following the same SAR, general SARs we said, whereby this can be substituted with a para substitution and methoxy group to have maximum activity. That's pyramine. Antazoline, that is the structure we have talked about. Thonzylamine, again, in place of the pyridyl ring, we now have the pyrimidine ring with retention of activity. And then also we have methapyridine. In methapyridine, again, we still have the pyridyl ring, because remember the pyridyl ring is responsible for maximum activity. Then our phenyl ring is replaced with the thiophene ring with retention of activity. So again, I hope you have followed, because even if you do not go through the SARs, that is, we can be able, even by looking at the structure,